Welcome back. Now we have looked at in our VMDL how the diffusion happens, and I do want to talk a little bit about confinement effect. As you saw that when we had reflecting boundary conditions, the blob or the particles were able to move faster because of the confinement. It's almost like when you have a smaller tube and the water is flowing through, it has a higher velocity, but when you make the diameter of the of your tube larger, then the velocity slows down, which is again you can look at from the fluid mechanics perspective and the Pascal's law perspective, etc. But if you look at in this case, as we made the boundary condition periodic, then it was almost like the particle moving through a very large bulk system. So, you saw the slowing down, and that slowing down is because almost now you have infinite diameter. Now, particles are moving back and forth, and they are taking their own time to settle down, because there is no confinement. As soon as there is confinement effect and the gravity is working, then you saw a very straight trajectory of the particle through the tube, and that is where you can think about the blood going through your arteries and understand that how the fluid mechanics will change and the diffusion of the blood will change based on the capillary effect that it will cause. So, and that is very important biological issue when the blood flows through your arteries and your veins. It depends on, and a lot of it is created by the confinement effect of the tubes, because that is the force that is allowing them to change the pressure, and that is where what we call is that blood pressure. And so, if there is a increase in the blood pressure or drop in the blood pressure, and this is where you can see that different particles going through these hydrocarbon tubes. And so, now you are ready to think about advanced problems like that, like blood flow through the arteries and veins, and you can do molecular dynamic simulation by creating this kind of and understand how the blood flow will change in different kind of situation. So, now let us move on. With this understanding, on your slide I have given you some of the other transport properties. I want you to look at these formulas carefully, and I will point that out, that in diffusion that we develop the Green-Kubo formulation, and these are all Green-Kubo equations. So, this is the same formulation, however, you will see what parameters are changing here. So, in this case diffusion is the velocity of the particles, because we are looking at diffusion. Now, if you look at shear viscosity, we are talking about shearing effect, which is what we call as their stress is shearing, and there is a stress which is causing the shear. So, if you look at the shear viscosity when there is a when there is a confinement effect and there is a shearing of the atoms through it, like you saw in the smaller tube, then you have to look at the stresses which are created due to the shear. And the shear effects are created because of the atoms close to the boundary of this confined tube are going to be at velocity 0, while in the middle they will have the maximum velocity. So, there is a velocity gradient, and that is causing certain stresses between the layers. And you know, the fluids are viscous, and there are viscous layers, and there is a shear between the viscous layers. So, when there is a shearing between the layer at 0 velocity and with a certain finite velocity, this is shear viscosity. So, if you look at in that case, the function is not velocity, but we are looking at the stress. So, the sigma is looking at x y, the stress in x y direction, and that is where if you look at, you have to then use the definition of the atomic stress, and that is where your Green-Kubo formulation has to first decipher the stress, but then if you look at again stress as time 0 and stress as time t in the shear viscosity with some of the other volume elements to it, now you can calculate the shear viscosity. And so, the correlation function now is stress correlation function, which is an important thing to look at. Now, when you go to thermal conductivity, now it is about half mv square, as you remember from the earlier part, that the temperature is related with the kinetic energy of the particles. So, half mv square was connected with the temperature. So, we know the velocities, again we are looking at the velocity, but now we are looking at the what we call as Q, which is the thermal flux. We are looking at the thermal properties now. So, we are looking at the flux at time t 0 and the thermal flux at time any arbitrary time t. So, again the same Green-Kubo formulation, time correlation function is now in terms of the thermal flux. And so, now if you look at, in this case the thermal flux have to be defined q in terms of half m v square plus some of the changes in the what we call is the potential energy. So, if you now look at the kinetic energy part of it, that will define you the thermal flux. Once you have defined the thermal flux in this formulation, all you have to then do is use the Green-Kubo formulation with the time correlation of the thermal flux at time t 0 and at arbitrary time t. And then you know that because we are calculating trajectories, we already know all the parameters to calculate the thermal flux. With that idea, we are able to create the thermal conductivity transport coefficient. And this is again the power of molecular dynamic simulation, is that because we have the trajectory of the atoms, we also understand the fluctuations caused by providing let us say a temperature or a pressure, which we are able to do in our different kind of ensembles like isothermal ensemble, which is a TVN ensemble, which is canonical, or isobaric and isothermal ensemble, which is TPN ensemble, where we can change pressure and temperature, and we can create those fluctuations and look at the dissipation of that over time period t. And with the time correlation function, we have now very good idea of transport coefficient. So, not only we understand now thermal properties like temperature, pressure and heat capacity, etc., we are now also looking at all the transport coefficient. Now, that really tells you a lot about the system, especially if you are looking at crack tip formation or ductile to brittle transition in the material to temperature. You need to know the temperature flux. As the temperature goes down, what is happening to the elastic constants, why they are stiffening, and from there, instead of ductile, which is the stress strain behavior where there is extension, now the extension is not possible at very low temperature, and then you have a brittle failure, and brittle failures are catastrophic, which you saw in the Challenger disaster. There was an O-ring which is made of hydrocarbon plastic, and at certain temperature that plastic became brittle, and so there were small little cracks in it, which let the air the gases go out, and that caught the entire Challenger into disaster of the fire. And that is very simple fact of that, the brittle transition. Now, you can understand that using the thermal coefficient, because as the transition is happening from ductile material to brittle under certain temperature conditions. So, you are looking at the changes in the behavior of structural properties under the temperature, and that is where transport coefficients are changing. So, this is where it becomes very important to understand very complex phenomena now using molecular dynamic simulation. So, now with the time correlation, where we are looking at the trajectory, we are now able to understand how things will happen in correlation. Now, we come down to what is called space time correlation, and space time correlations are now going to connect with not only the time correlation, but also the space correlation. So, that means we are going to look at the positions, and those positions are important now for a system of, let us say, n particle, as is given on your slide. The number density at the position r and time t can be expressed. So, now think about system of particle in the box. They have positions r, and so there is a volume v. So, if you divide number of particles with the volume, then you understand that there is a number density. So, number density now can be defined in terms of r and t, which is the position of particles, and t, because there could be a movement of the particles. As the particles move, there is a change in the density. Think about your voice going through the air medium. It is creating this wave where there is a higher density and lower density rarefication, which is the wave motion of my voice through this air medium. So, similarly, if I look at that box and see this wave of particles moving with different densities, that is where we can look at what we call as space-time correlation function. So, we just start with a simple definition first, and then we will go into detail. So, suffice to say that while we are able to look at a lot of this correlation function purely from the time correlation perspective, we also now can go further down and refine our molecular dynamics understanding of the material by doing what is called space-time correlation function, which is called density correlation function, because in space-time the material properties are changing. That means their density is changing with respect to time. Thank you.